in this technology, we are isolating a piece of skin from burn patient from the unwounded side of the body, and then we expand them in the lab and in a GMP facility that we have here in the hospital. And then we make a cell sheet that you can see here nicely, and then we put them back to the patients. This technology has been there for more than 4 decades, but many groups in all around the world are using this technology for burn patient. However, this technology has some challenges. For example, handling the cell sheet or CA is very challenging, and also it takes time to develop cell sheet, and it could be up to 4 weeks. And the other strategy that we are using when we don't have enough cells, or when we don't have, or the burn site is very intensive, we are using the artificial skin substitutes or dermal templates. One of the templates that we are using in our hospital at the moment is using the Novozor or biodegradable temporizing membranes. And as you can see here, when we are using them in the long term in the patient with the extensive burns, we can see enhanced regeneration of the tissue and sufficient scar outcomes in the patient, which is very important in the long term. As Bill mentioned, lately we started a research hub. We call them as a Herzog Biofabrication Institute. And the idea is to utilize the additive biomanufacturing techniques in wound cares. And for today's presentation and today's audience, I will talk about 2 of the streams that we have. One of them is about developing biologically active wound dressing. I call them as a cellular dressing or 3D printed cellular dressing. And the other stream is about development of orthosis or spleen for burn patient as an important thing. As some of you may know, wound dressing has been there for many centuries. And the idea for wound dressing is to avoid any infection and also to protect the wounded site from the trauma, and also absorb the drainage that we have, and those allows oxygen exchange and nutrients, or let's say the drainage to come out of the wound. Much effort has been made on the development of the dressing that works by or manipulate the biochemical conditions of the wound, and investigating the biomechanical or mechanical properties of the skin and wound that has received less attention. This is something that we are interested, and we are interested in developing some dressing that can manipulate the biomechanical factors in the wound area and enhance the skin regeneration and wound healing. Just by looking at the skin, we can see that the skin is a viscoelastic material that has a non-linear elastic modulus that you can see here. By applying a bit of load or low load, we have much deformation, and this coming from the fibril proteins that we have in the skin, which is mainly collagen and elastin. And by deformation of the skin, we have fibers that are aligned together, and at the end we have the rupture of our fibers, and the skin is ruptured. By using this approach and by looking at the nature, we aim to develop some biomimetic dressing. And the technology that we used here, or the machine that we used here, is called melt electrowriting. Melt electrowriting is a new technology that has been used or we call them as a high resolution advanced manufacturing technique. And in this technique, we have a print head that you can see here. And in the print head is occupied with some melting system that we can put the polymers there, and then we print the polymer here into the collector that we have. And as we can see here, by using the 3D printing technology, we call them as a melt electrowriting, we can deposit fibers in the high resolution, in the low, by micro or nano resolution, and the fiber develop some scaffold or some dermal template, as you can see here. And then this is how the melt electrowriting machine is working, that you can see the nozzle is moving and is also connected to the computer. And we developed we first design our model using the CAD, and then we put them into the machine. As I showed you before, the collagen and elastins are like this in our skin, and scaffolds that we could create here, you can see that it has various structures and it could be very porous. And we found that this is the SEM analysis of the scanning electron microscopy image of our scaffolds. And this is CT image, micro CT image. As you can see that we have porosity of over 90%. The porosity is very important for regeneration of the human tissues, specifically for the skin, because it allows vascularization and also it allows the tissue infiltration. And specifically for the dressing, we need to have the gas exchange and also drainage of the wound. And when we check the mechanical characteristics of our construct, our 3D printed construct, we found that the polymer that we, just before going that, the polymer that we used here, we used medical grade polycarbolactum or mPCL. Some of you may know that the PCL have been used extensively for development of the scaffold and 3D printed construct. And by doing the tensile stress analysis, we found that in both radial and circumferential direction, we have similar characteristics between our medical grade PCL and the dorsal skin of the rat. However, and this is similar to our human skin that we have, which is, however, when we did the quantitative analysis, we found that the numbers for, let's say, ultimate tensile strength or high tensile modulus are much less for our scaffold compared to the skin. Let's say here, the rat dorsal skin. It is important to highlight that here we have only fibers and we don't have the cells, because in our body also cells contribute in the mechanical properties of the skin. And also the melt electrowriting technology has the modularity, and we can improve the design or improve the thickness of our scaffold to develop some dressing or some scaffold that is suitable for different species and for different anatomical locations. PCL is very hydrophobic polymers, and for medical application, we need to have something that is hydrophilic. Then we did the plasma treatment by using the oxygen and argon, and we found that the polymers after plasma treatments are highly hydrophilic. Then we decided to because we are interested in developing the cell dressing, then we decided to seed our construct, our PCL construct, with some mesenchymal stem cells. In this study, we used gingival mesenchymal stem cells because those are an abundant source of the gingival tissue, is abundant source of stem cells. And there are much similarity between mesenchymal stem cells that we can isolate from gingival tissue compared to other tissues that we can get in a body. And also it has been shown that the gingival stem cells resembling the fetal tissue healing mechanism. As you can appreciate, the wounds that we have in our mouth in this area are healing very fast compared to the wound that we have in our skin. Then we seeded our cells, and as you can see here, the 3D printed mPCL dressing that we developed using the melt electrowriting could support cell attachments and cell survival and cell expansion. One of the things that we are very interested is about creating off-the-shelf product. And in this regard, many cryopreservation technologies has been developed over the last decade to see that how we can cryopreserve our tissue engineered construct. And in this study, as you can see here, we also use different methods and different cryoprotectant to freeze down our construct that we developed, and we freeze down them and with different methods. One of them is just a DMSO plus 10% FPS, which is commonly used everywhere. And also we use different products. And we found the cryo store by using the gradual freezing, just 1 by 1 degree, and using the cryo store as a cryoprotectant, we have enhanced survival of the cells. And as you can see here, the green represents the live cell and the dead represent the dead cells. As you can see here, this is before presentation that I showed in the left panel, and this is after preservation, after cryopreservation, that we can see that most of the cells that we seeded, we frozen and then revived them, they can survive in the culture. And then we decided to assess the performance of our mPCL dressing in an excisional splint model in the rat, in the cutaneous wounds. And because of the high surface area and high porosity and high hydrophilicity of our scaffolds, we could see that the scaffold can attach to the wound area. I mentioned earlier that it is very important. We need to have integration between our construct and the wound bed area. And also the construct that we developed is suturable. We can suture that, and then we use the splint around that to just avoid any contraction. The metal splint that you can see here. We also use the 3D printed construct as well. And then we tested them in the animals where we have no splint alone or splint with the medical grade PCL that are alone or with and without cells. And one group, we have a cryoprotected cells. And for dressing, this is very important that our dressing avoid any infection and also have a beautiful cosmetic result at the end. Here you can see that in our microscopic image, I just briefly talk about that. I don't want to go into the detail, but after 42 days, we could find that when we don't have any splints, we have big scar tissue, which is because of the quality of the regeneration that we have. However, when we are using the mPCL scaffold and then we are using the cryoprotected tissue engineering construct, we found that we have reduced size of scar tissue formation. And here we found that the fresh tissue engineering construct